What's up, guys? This is Mr. O'Brien. In this video is part one of Chemical Reactions, Unit 4A. We will talk about the information in text in the section 10.1 of your textbook. This is for both college prep and honors. So let's get started. So what's a chemical reaction? Well, consider the pictures below here. Take a look at the way steel, like a steel block, changes over time, over a course of a year. And take a look at the way a tree changes over the course of a year, right? Do you notice changes that takes place? Well, in the steel, right? The steel reacts with the oxygen in the air to create this film, this like reddish, flakish film, which we call rust. It's a combination of iron and oxygen. Here in the picture that we see to the trees, the chlorophyll gives a green color to that we identify the leaves with. But over the seasons, because of the changing amount of daylight, the chlorophyll starts to degrade, starts to change and break down into smaller molecules. And hence we get the changes of the colors from yellow to orange to red. Now, again, chemical reactions is this process that changes the initial composition of stuff into new ones. So what indicates a chemical reaction took place? So if you take a look at some examples here, we identify changes in heat and temperature from combustion reactions. We have a color change from the burning of marshmallows to create the s'mores. We have the formation of odor or gas bubbles, like in decomposing trash, that's stinky stuff, or even when a cake starts to rise as you put it in the oven. And then we've probably seen these formation of precipitates, like these liquid solutions, when you combine together, form a solid. So there's a lot of examples of evidence that tells us a chemical reaction takes place. I would like you to pause for a moment and take a look at these three examples that you see here. Could you identify which of these are chemical reactions and which are not, based on what we just talked about of chemical reactions and what they're made of? So how does a chemical reaction look at an atomic level? So at an atomic level, the atoms and the molecules of the reactants, right, of our ingredients, these atoms somehow need to be freed up so that they can, keyword here, rearrange to form new products, new stuff. But how do they get rearranged? Well, they get rearranged when the bonds between them initially are broken. And as they're broken, they're free to move around. They combine together, rearrange to form a new substance. In this video here that we saw in class, we have breaking up of carbon dioxide and water to create glucose and extra oxygen molecules here. So how do we identify, how do chemists represent these chemical reactions? Well, we represent them using equations. And so what does that look like? Well, let me give you an example. Take a look at this image here, this quick little clip. So this clip is showing you a chemical reaction. We can tell a chemical reaction takes place because of change in color, right? Between solid iron, which is the steel wool, placed into a container of chlorine gas, which is this yellow kind of film here. When they combine together, the atoms, the molecules are broken up and the atoms are rearranged to form new stuff, which is this iron 3 chloride. So how do we represent that in an equation? Well, first we have to split up what we call the reactants, which are the ingredients in a chemical reaction. So we split them up and then we show with an arrow what they produce, which we call a product, the new stuff that gets created. And in this case, there's only one product, but sometimes chemical reactions can make multiple products. So we have to split those up, and we split them up using the plus sign, right? Well, beyond this, we don't just write reactants and products. We actually have to identify what they are. So the reactants here are identified with their words. And in addition to that, they're identified with their states of matter. The solid indicates S, the L indicates liquid, the G indicates gas, and the AQ means a water-based solution. So like salts, which are typically solids, when you dissolve them in water, they're actually a water-based solution. It's important that we identify these states of matter because consider the idea of making a salsa. Well, you know you need tomatoes and you know you need like cilantro and all that stuff. But what do? Do you use a whole tomato? No, you got to chop it up or you got to make it into some sort of like pulverized slush, right? But we go beyond these words, right, and start to use formulas, right? Formulas. In this case, iron here is given as Fe. Chlorine is not identified as Cl because, as you know from semester 1, Cl has 7 valence electrons, and so you can't have 7 by itself. So that's why chlorine, which is covalently bonded, has to be as 2. And again, this is just like for anything with hydrogen, H2, O2, F2, any of those nonmetal gases have to be diatomic, we call it. And then iron 3 chloride is identified here as FeCl3. And what this actually shows us is that this is a representation at an atomic level of what it means. You have 1 iron atom, 2 chlorine atoms, right, with 1 molecule, as you can tell, and 1 molecule or 1 compound of iron 3 chloride, which is considered of 3 chlorines and 1 iron. Now let me pause for a second and ask you this question. Can you count the number of atoms based on this? And do you see an issue with the way this is written? Well, if you see the issue that the atoms are uneven, you might be wondering, well, what's wrong with having an uneven chemical equation, right? Well, consider this problem, right? If you want to make Aunt Jemima pancakes, which are delicious, right? And you know that you need milk, you know that you need the mix, and you know that you need the eggs, and you know that you need the cooking oil, could you create the same tasting pancakes that Aunt Jemima claims that, or the taste? And the reality would be that you would not, because you don't know how much you need, and you don't even know how much you're going to make. Maybe you make 5, maybe you can make 4. You don't know because you don't know keyword the amounts. It's the amounts. And so real chemical reactions and real chemical equations have to tell you the amounts of ingredients that you need, right, as well as the amounts of products that you get. In this case, the recipe here calls for 1 cup of milk. I'm sorry, 3/4 cups of milk, 1 cup of mix, 1 egg, and 1 tablespoon of oil, and that will get you 12 pancakes. If you follow that recipe, your pancake should taste the same as the Aunt Jemima pancakes listed on the box. So the law of conservation of mass is really important when it comes to writing chemical equations. And the conservation of mass essentially says that whatever you start with will always be present in your products, and you're not going to make new stuff, and you're not going to destroy stuff. And it kind of sounds a little strange because, like, if you burn paper, right, or if you see a firewood burning, you kind of say at the end that, hey, there's like less solid pieces, right, as you see in this picture. But we have to understand that the solid piece that visually has gone away has gone into a new form called gas. And so even though it might be deceiving to the eyes, the gas still has mass. And if we were to capture everything, it would still be the same mass as your starting reactants. So how do we check for law of conservation, right? Well, let's go back to that same problem that we talked about earlier, the iron with the chlorine gas, right? The first thing that we got to do is we got to count the number of atoms in the reactants. So in this case here, I'm going to count the atoms. I'm going to show you how I do that. So I count as 1 iron below. I count this as 2 chlorine atoms. And I kind of split up the reactant side with the product side by the arrow and identify that I have 1 iron and 3 chlorines, which kind of looks like that. Now, this is not equal. There's 3 atoms of chlorine here, and there's 2 atoms of chlorine here. They are not equal. So how do we make them equal? Well, we have to add these things called coefficients. And coefficients are the whole numbers that are placed in front of the reactants to balance out the number of atoms. So let me show you here. So in this case here, I got to figure out how to make 3 chlorines equal to 2 chlorines here. So what I do is I'm going to go ahead and put a coefficient of 2 here to find a common factor of 6. So I'll change that to 6. I'll change that to 2. And you might be saying, oh, dude, I made it even worse. But that's what happens in a balanced equation. You got to actually balance both sides multiple times. So I'll make this a 6 by putting a 3, and that changes that to 6. But then I have to put a new coefficient on the reactant side because I have 2 irons. So I'll put a 2 here, and there is my new chemical equation. 2, 3, 2. And please notice that I did not change subscripts. I cannot change these small numbers here That's a big no-no. And I cannot add small numbers here either. I can only add coefficients. So let's try this example out in the college prep level. So in college prep, I'm always going to give you the formulas for the reaction. So let's go ahead and write this out. When we write out the equation here, we recognize that potassium chloride is your reactant. And it's going to decompose yield. Here's the arrow sign for yield. A solid sodium chloride, which is given to you here, or potassium chloride, and oxygen gas, which is given to you right there. Now let's count the number of atoms up. 1K, 1Cl, 4 O's, 1K, 1Cl, 2 O's. Now clearly the O's are not balanced here, right? So we need to put a coefficient here that will make them equal. If I put a 2 there, that changes this to 4, and now it's an equal reactant, equal equation. The number of atoms are the same on both sides, right? So you try this out for a college prep. If you're a college prep, try this one out, see if you can figure that out. And then for my honor students, I will not provide you the formula. It's really important that your skills on formula writing are to par, because if your formula writings are not good, then you won't be able to balance a correct chemical equation. So how do I write this? Well, you have the reactant here as sodium oxide, Na2O. Remember that Na is a +1, right? And O is a -2, so we need 2 NAs for every 1 O. And so chlorine gas is any diatomic non-metal gas, always written as twice. And same goes with the oxygen. And then we separate them, right, with sodium chloride. Now, sodium chloride is given to you as NaCl, okay? Now, so what we're going to do here is we're going to also try to balance the law of conservation. So we have 2 NAs, and we have 1 oxygen. We have 2 chlorines. We have 2 oxygens. We have 1 Na, and we have 1 chlorine. So we need to balance this out. So I can see that 2 chlorines are not balanced there. So if I put a 2 here, that changes this to 2. That changes that to 2, right? And if I take a look at here, it seems everything's balanced except for the oxygens. So this won't work. This 1 oxygen won't work. So we got to change this coefficient. There's a 1 here. For everything that you don't see here, there's a 1. So we put this at 2. We'll change this to 4. And we'll change that to 2. Now it has to change back again. And we'll change this to a 4. We'll change that to a 4. And we'll change this to a 4. And now we got to change this guy to a 4 as well. But notice that we don't change the oxygen. The oxygen is still 1 here. We don't change anything. So here's our lowest ratio, 2, 2, 1, 4, right? So if you take a look at that equation here, balanced equation, try this problem here for your honors. Again, this is only for honors, right? Only for honors, and this is only for college prep, okay? So try that out. If you have any hard times, hit me up at the tutorial. Here's another set of problems that are good for both college prep and honors students. So try to see if you can figure these ones out. If you have a hard time, hit me up at tutorial. And then I want to show you a shortcut to balance chemical reactions with polyatomic ions. So consider this one, right? So, some students will call this like, oh, we have 1 silver, right? We have 1 nitrogen. We have 3 oxygens. We have 1 copper, right? We have 1 copper. We have 2 nitrogens, right? We have 6 oxygens, and we have 1 silver, right? But there's an easier way to do all that than just by identifying the number of atoms. We can identify the groups of atoms if the groups of atoms of reactants are the same on the reactant side as in the product side. But you got to recognize how many we have, and hence a parentheses. Whenever the polyatomic has a parentheses around it, then you know there's more than 1 set. So here we have 1 silver, 1 NO3, 1 copper, 2 NO3s, and 1 copper and 1 silver. So the NO3s are not balanced. And so what we do here is we just write a 2. We have 2 silvers, and we have 2 nitrates, and we have 1 copper, 2 nitrates, and then 2 silvers. And that's actually a lot easier than counting the individual atoms up. So practice this problem out, these 2 problems with the polyatomic ions. And again, this is both for college prep and honors. And so if you have these, if you use a shortcut, you'll find that this becomes a benefit to you. All right. Hit me up at tutorial if you have any questions. Thanks.